restricted army base, a specially trained recovery team prepares to fly deep into the Utah desert in the dead of night. Their mission? To rendezvous with a traveler from outer space. A traveler returning from a 7-year voyage of nearly 3 billion miles and carrying a precious cargo. Particles from the beginning of time, samples of stardust. It's the final phase of a 7-year mission, and this is its most critical moment. A small space traveler, no larger than a suitcase, is returning home with a cargo of ancient cosmic treasure. The high-tech capsule of NASA's Stardust mission promises to contain pristine specks of comet dust. Dust that may hold the answer to the beginnings of life. The work of scientists all over the world hangs in the balance. Will Stardust succeed in its mission? Will the capsule survive its fiery re-entry to Earth with its contents intact? No one has more at stake than these two men. They want to be the first to hold pristine comet dust in their hands. Don Brownlee and Tom Duxbury have invested more than a decade of their careers to this mission, and it's down to the final moments.
We've been working this mission for about 10 years.
Ask a mother one day before a baby's born how she feels.
You know, 10 years ago, this day would never seem to come.
This is a mission for the record books. Stardust has clocked more miles than any other return mission. Its capsule will be the fastest man-made object to ever come crashing through the Earth's atmosphere. And it's the first attempt to catch a comet and bring home a snapshot of our solar system from the beginning of time.
Some of the samples we're collecting are older than the sun, older than the planets, and are interstellar grains that were incorporated in the solar system and in comets 4.5 billion years ago when the solar system formed.
Scientists hope this comet dust will tell us about the origin of our solar system, how water and even life came to our planet. The success of this whole mission rides on the spacecraft itself. The man responsible for building the spacecraft is Joe Valinga.
The Stardust mission can kind of be summarized as a 3 billion mile, 7-year trip from Florida to Utah, with a little comet encounter thrown in between.
Alan Chevront is the spacecraft team chief for Stardust. His job is to take care of the spacecraft.
Stardust was designed as a 7-year mission to visit the comet Wild 2 and have a flyby of it, collect dust particles, take some pictures, do a mass spectrometer, and then return the capsule to Earth.
A big job for a spacecraft no bigger than a phone booth.
We had to design the spacecraft to consume very, very little power at that distance, as well as have solar arrays large enough and efficient enough to operate and provide the solar power out at the max distance from Earth.
It had to be energy efficient.
In terms of power consumption, Stardust takes basically 180 watts. So your hair dryer you use in the morning is almost 5 times the power draw as the entire spacecraft.
Small and efficient. But Stardust had to be tough to perform in the treacherous environment of space. Unpredictable events like solar flares can devastate the electronics and stun a spacecraft. So finding the fastest route to the comet was a #1 priority.
0 and liftoff of the Stardust spacecraft.
Before the spaceship even left the ground, they needed a flight plan to intercept a speeding comet and return to Earth safely. It's like trying to throw yourself a frisbee. You just have to hit the spot where you expect to be 7 years from now. To get there, the spacecraft flew 3 times around the sun. On its second pass, it hitched a ride using Earth's gravity to swing it out halfway to Jupiter, where Comet Wild 2 was passing through. There's no human on board this mission, so navigator Shyam Bhaskaran flies the spacecraft from Earth.
we're like a giant map quest. What we do is we watch the tracking data come down from the spacecraft to our tracking stations, and then we determine where the spacecraft is currently. We know where it wants to go, so we then plan and execute maneuvers to take the spacecraft to where it wants to go.
Shyam periodically fires thrusters to change speed and direction. Too much or too little, and you miss your target completely.
So even though we know pretty well where it is at any given moment, the prediction of where it's going to go in the future is going to be a little more challenging because of these small forces that act on the spacecraft continuously.
In January of 2004, Stardust was able to photograph its target in spectacular detail.
The great thing about flying by comets is that you don't really know what to expect. Nobody's ever seen this one before. We were really excited to see exactly what this looks like.
And the scientists were not disappointed. The comet's surface is riddled with craters, bizarre escarpments, jets of gas, strange pits and cliffs. No one had ever seen anything like it. But Stardust wasn't there just to snap pictures. Its real mission was to capture the dust and bring some of the comet back to Earth.
Every picture you've ever seen of a comet is not really a picture of a comet. You cannot see the comet in that picture, even though it's labeled in your textbook as a comet. What you're seeing is the comet coming apart. So you see the tail, you see the coma, but you don't see the body.
Comets are relics from the early solar system, frozen in time, but they remain frozen only when away from the sun.
And the spectacular things we see in the sky, we call comets, are actually comets disintegrating due to solar heating. The heat from the sun volatilizes the ices, which escape as gas, and that also releases dust, comet dust, into space.
An active comet might look beautiful from Earth, but some of those particles could destroy a spacecraft.
For Stardust to collect dust, we needed the comet to be active. And so there's a trade between safety and science.
We tried to fly by at a distance to balance the need to get really close to collect particles, but not so close that we would have a reasonable probability of being hit by a particle large enough to kill the spacecraft.
Like a medieval knight, the spacecraft carries protection called a Whipple shield.
So what we have is a bumper shield that explodes the particle, and then 3 layers of Nextel, which is a ceramic cloth below them, and then the next layer is the front panel of the spacecraft, or the solar rays.
Hiding behind its shield, the spacecraft passed through a hailstorm of particles.
Now, to our great pleasure and enjoyment, our spacecraft flew through this unbelievably hostile environment of these dust particles coming at us at 6 times the speed of a bullet.
These dangerous particles were just what Stardust wanted. To capture them safely and survive, the team developed a strategy.
Aerogel is key to Stardust. It's our dust collector. It has such unique characteristics, the lightest weight material in the world.
This is a piece of aerogel. It's about the same size and dimensions as those used for the Stardust mission. It's 99% air and about 1% silicon dioxide.
Almost totally air, yet unbelievably strong. Aerogel acts like a butterfly net in space.
So basically, the particles are coming in at 5 kilometers or 6 kilometers per second. And what they do is when they encounter the material, they embed themselves in the material. So basically, I say to people that it's like catching a bullet in a bale of hay.
As the particles penetrate the aerogel, they create a carrot-shaped track. The aerogel melts and forms a glass sphere.
Really keeping them pristine, intact and pristine.
Aerogel is packed into a kind of ice cube tray shaped like a tennis racket. Stardust thrusts the tennis racket in front of oncoming particles, collects the samples, then seals everything inside.
We went to a clamshell approach where the capsule opens up like a clam does. That gives us a uniform seal all the way around the circumference of the capsule.
All told, Stardust is bringing back a pinch of comet dust, but the possibilities of what it contains have scientists anxiously waiting. After all, these are the first samples to come back to Earth since the early days of the lunar missions. For the first time since the lunar missions of the 1960s and 70s, a space capsule is hurtling back to Earth with solid particles from outer space.
The fabulous thing is that theory and imagination aren't so important when you actually have the sample in hand. A really fascinating analogy, I think, is Apollo.
At the time of the lunar landings, there were all kinds of theories about the moon's history and geology. Samples of moon rocks helped settle those questions. This time around, it's a 7-year round trip to the comet Wild 2 and a spacecraft flyby to snatch dust samples from the comet. It's a 3 billion mile odyssey called stardust.
When we look at these particles that just came hours before off of the comet, we will then try to verify a lot of the theories associated with comets. It's believed that comets brought a lot, if not most, of the water that's on Earth and a lot of the chemical building blocks that's required for life on Earth. And in fact, we believe that all of us walking around, the plants, animals, are basically stardust, cometary dust.
It's a remarkable thing that every atom in the Earth and every atom in our bodies, in the chairs, and we sit on the cars we drive, we're all in stardust, interstellar grains, before the solar system formed.
But comet dust is everywhere.
We have tons and tons of cometary dust falling to the surface of the Earth daily.
Stardust space.
So why fly 3 billion miles to get a sample of the stuff? Quality control.
One of the problems is we do not know which comets these came from, when they came, and what changes have occurred as these particles have gone through space and through our atmosphere.
The scientists want samples hot off the comet.
They just left the surface of the comet hours before we captured them. So for our case, it's typical of a scientific experiment. We've controlled the environment.
The pristine samples have not been changed by heat or ultraviolet radiation.
In the case of comets, we expect that many of those stardust grains at the very edge of the solar system, which is very far from the sun, in very cold conditions, that those were preserved.
Samples preserved in their original condition. That's why the scientists can't wait to study them.
They're kind of a history book for the solar system, a library that retained the records of our formation.
So the spacecraft speeding back to Earth has done much more than take a 7-year stroll through space.
Stardust went, halfway to Jupiter, but what it really did, it went to the edge of the solar system 4.5 billion years ago, because we think that's where we're going back in space and time.
A comet trapped in orbit around the sun is doomed. Yet new comets appear on a regular basis. It's as if there's some great cosmic parking lot out there.
And the classic reservoir is called the Oort cloud, which is very, very far from the sun, thousands of times further from the sun than the Earth is.
Fortunately for the Stardust team, there's a closer source of comets.
There's another reservoir that's been more recently known, and that's called the Kuiper Belt, or Kuiper Belt. And that's a band of material just outside the orbit of Neptune, out around where Pluto is.
The Stardust project had a date with what appears to be a Kuiper comet. Now, after putting up with particle attacks and solar flares, it's a matter of surviving the return trip.
We sat down as a group and tried to identify everything that could possibly go wrong that would impact us from releasing this capsule. And we came up with over 360 items.
One reason things could go wrong is speed.
We come back very, very fast. We come back much, much faster than the Apollo missions when they come back from the moon.
The spacecraft has to come back to Earth on a very specific day within a few seconds of a specific time. Otherwise, it will never land in the desert of Utah. Once again, navigator Shyam Bhaskaran is in the driver's seat.
And so at some point, we have to basically give it the instructions to the spacecraft to do a maneuver to take target to the right spot.
There is no margin for error. Make the correction at the right point in space, or send the precious samples off into the galaxy.
And that's going to be the biggest challenge returning to Earth, because we have a very narrow corridor to hit to come back to the Utah test range.
The Stardust spacecraft has been the workhorse of the mission for 7 years, but it will never return to Earth. Instead, it will release the capsule to complete the mission alone. About 4 hours before the expected impact, the release sequence will begin.
We will cut the cables that connect the capsule to the spacecraft, and then we fire the bolts that hold the spacecraft, and there are 3 springs that will push it off, and it follows a cam, and as it's being released, it will impart a spin.
Once the re-entry starts, there will be no time for corrections.
At that point, our job is effectively done because the capsule is on a ballistic course. If we cannot make course corrections, we can't even track it. It's basically coming in whether we like it or not.
The capsule will enter Earth's atmosphere at 28,000 miles per hour. 10 times faster than a speeding bullet.
It's coming in very, very fast, so it will light up the sky. There'll be a big streak from over the coast of Northern California as it streaks across California and then over Nevada into the deserts, over the deserts of Utah.
And the heat shield only works if it's pointed in the right direction.
The capsule shape becomes unstable when we go subsonic. The drogue chute stabilizes the capsule, keeps it stable until we pop the main chute at about 12,000 feet. It also helps slow the capsule down.
With the capsule drifting safely towards Earth, the command center will send the spacecraft one final course correction. It means farewell.
The spacecraft then is diverted to a trajectory which will never come back to Earth, so we don't have to worry about it hitting the Earth again in the future.
Unless someone comes up with more money and a new mission.
In that regard, you can go back to the Pioneer spacecraft, was launched in the early 70s. Up until a couple of years ago, they were still talking to it.
Most likely, the spacecraft will be ejected from the solar system to cruise the galaxy, a kind of interstellar ambassador or starry messenger.
There are almost 1.4 million people that signed up on the web and have their names engraved in a little silicon chip on the spacecraft. It's at least intriguing to me to think that when the Earth is gone, and even the sun is no longer the sun we see now, it becomes a white dwarf star, those names and stardust will probably be wandering around the galaxy somewhere.
With its ride heading off to the stars, all that remains for the success of the mission is a safe recovery of the capsule. And that's easier said than done, because before the big night, the recovery team must practice over and over, like the cast of a show working toward opening night.
Everything has to be done by the numbers. If it's not, they'll shut the mission down. You only have so much time to reach the window for this thing to get in.
These are the men and women of the Stardust recovery team. They will be the first to have human contact with the Stardust space capsule in more than 7 years. When it comes streaking through Earth's atmosphere, scientists are hoping it's carrying a precious cargo of comet dust. The final success of this mission will be up to them. This is rigorous training, a result in part from experience gained from Genesis. That capsule came crashing into the Utah desert, carrying a payload of solar atoms. The capsule's parachute failed to deploy. So for Stardust, it's train and retrain. A mock-up capsule and a helicopter play starring roles in this drill. They will rehearse in the dark, but to give them a head start, they first rehearse in the daylight hours. Job number 1 is locating the capsule. A beacon on the replica beams back GPS location coordinates. On this rehearsal run, the team has no trouble securing the target. If things go as smoothly as this on the night of the landing, scientists will be one step closer to unlocking the 4.6 billion-year-old secrets that lay embedded in comet dust. But catching the dust isn't the only way to study comets. And Stardust isn't the first NASA mission to try taking a closer look. Deep Impact was the unprecedented mission designed to smash a probe deliberately into the side of a comet.
Okay, that's good.
Dr. Peter Schultz was co-investigator for the Deep Impact project.
The Deep Impact mission was a cratering experiment. By watching the process, by actually watching the ejecta come out, watching how it evolves, we're able to deduce what the nature of the comet's surface is.
Until this mission, astronomers had no way to see inside a comet.
We don't know what a comet surface is like, and until Deep Impact, all we could see were images, not even high-resolution images prior to Deep Impact.
But Deep Impact changed all that. Like a space-going geologist, the Deep Impact probe dug beneath the surface of the comet, exposing riches from the beginning of time.
We are exposing material from below the surface that has not seen the light of day for 4.5 billion years. It's the stuff that we know we probably don't even see from telescopes. It's been hidden, archived.
And what it's revealing is helping Dr. Schultz paint a picture of a comet's surface.
I think of a comet similar to what happens in the springtime in the Northeast when the snow begins to go away. And you watch the snow disappear, and the place that is left over is the place where you had dirt.
While Stardust is looking at the individual comet particles, Schultz is looking at the structure of a comet's surface and the material underneath. Here in his lab, Professor Schultz continues to piece the puzzle together. He's trying to create Deep Impact all over again, kind of like a cosmic chef in a science kitchen. He recreates the space experiment with this: a giant vertical gun that combines hydrogen gas and gunpowder to make craters.
The vertical gun allows us to fire a bullet at velocities very close to the Deep Impact velocity, around 4 miles per second. So when we slam into a target, we're able to actually see the crater form.
Today, he's testing the idea that the comet has a soft exterior and is hard underneath.
Okay, that's perfect. We're really interested in finding out if the comet is made up of a hard, rocky material or if it's made of a fluffy, soft, like sand or maybe powder. And based on work that we had done before, we knew very likely that it was going to be powdery.
Schultz starts by putting together the ingredients resembling a comet, which will serve as his target.
Ideally, you'd like to use ice, dry ice, organics.
Next, Schultz enters the vacuum chamber where the collision with the comet-like materials will take place. He carefully lays down the hard and soft layers believed to resemble the comet.
So what we need to do for this shot is to see if we can't put in a layer of highly porous material on top of less porous material and see if we can reproduce what we saw for Deep Impact.
The chamber is sealed, the air removed to replicate space where there's no atmosphere to slow scattering debris. After the gun is loaded with a small glass bead, it's carefully aimed. When it goes off, it will fire the projectile 10 times faster than your average bullet.
There we go. We're armed and gated. Photo beams.
If Schultz has the recipe right, we should see another Deep Impact recorded on high-speed video.
I gotta see this. All right. Oh, that is gorgeous. Oh man, that's spectacular.
The results are preliminary, but the collision in the lab seems to resemble the real impact in space. It also suggests what Schultz predicted in the first place. The comet has a soft outer layer.
So now we're seeing excavation of the underlying material.
Ultimately, Dr. Schultz wants to know why no two comets look alike.
They're dramatically different. Why? It could be that some of them have resided in a different portion of the solar system for a longer period of time. Could be that one was captured by Jupiter and was thrown into the inner solar system, got bashed around, and then went back into a place that was a safer place to hide until once again it came in visiting us in the inner solar system.
He may never get to visit a comet, but Peter Schultz plans to go along for the ride.
Comets have been fascinating, whether you're a kid or a scientist. I mean, I saw one when I was 12 years old, and I've been hooked ever since. Comets are just beautiful to look. They're mysterious. They are foreboding. They started wars, they've ended wars. But on the other side, comets carry with it the ingredients for life. The ingredients including water, organics. We are comets. We are made up of the stuff that make up comets.
While some people who get bitten by the comet bug become scientists, most remain amateur fans. Then there's the select few who make comets a lifelong passion. Head south out of Adelaide, Australia, and point yourself toward the sea. After an hour, you'll find a tiny town with a galactic secret. Driving through Yankalilla takes this long. It's not the kind of place you might expect to find a man like Bill Bradfield.
Well, all the ones I discovered bear my name. I'm the sole discoverer, 18 altogether.
Bill is a comet hunter.
I expect to find another one sometime in the near future.
In all, he has found and named 18 comets. More than anyone else on the planet.
I guess perhaps I persevered more, or maybe made an effort, in particular, getting up in the morning.
His remarkable find spans 3 decades, beginning in 1974. And the secret to Bill's prolific success? Well, he's very nonchalant about his technique.
Just a matter of sweeping the sky and changing the elevation by a little strip so you can gradually going up.
Now, you might think someone this good, by the way, Bill is a retired rocket scientist, might also be using the very cutting edge of technology, trying to squeeze every advantage out.
It's been lying around for about 2 years and mice have chewed at and crapped on it and so on, but anyway.
Well, you'd be wrong. Look closely at Bill's telescopes and you'll find a man of simple means.
Well, I built this in 1970. I was when I got the bug.
This is his first telescope.
14 of my discoveries were made with this one.
Complete with twine, a juice bottle cap, and a lens that is more than 100 years old.
Back in 1970, I paid $60 for it. Second-hand wood and bolts and nuts, yes.
He says the secret was in his wooden stand.
You can't do an hour's or 2 hours glued at the eyepiece and have a strained neck or whatever. You've got to have comfortable observing, and this gives it to you.
Comfort is important, but knowledge and patience are key. The hunt for a comet is measured in thousands of hours spent alone.
I discovered my first one after 260 hours.
Looking for something that doesn't belong.
But when you come across something you don't remember being in that spot, the excitement starts from that moment. It's a comet.
Today, Bill uses a more modern, more powerful telescope.
F5.6 mirror, Newtonian-type telescope.
It uses a collector mirror to focus the light and allow him to see objects even farther away.
You see the mirror down there? Yes, and my reflection.
Now, he still built this one himself. The wood came from a scrap pile. The precise collector mirror came from California. It's bulky, awkward, and not particularly beautiful, but it works.
3 discoveries made with that one, including the one last year.
On any clear morning or clear night, the best place to find Bill is loading up and getting ready to go hunting. Bill has spent so much time out here with his first telescope, he figures he's seen it all. So the new telescope, built a few years ago, is allowing him to see farther and fainter objects.
I think the chance of discovering a comet visually, the old way, my way, are getting near zero. I probably might win another one because I'm still able to focus on some part of the southern sky. Okay, ready to go. All I have to do now is take the lid off. And there's the hook of the scorpion at the end there.
With his weathered star chart, complete with decades of notes, the hunt is on.
I do a sweep, which is limited in azimuth.
Bill spends much of his time looking just above the horizon, in a place big modern computer-driven telescopes can't see because of their inability to tilt.
Those areas very low down are still prime territory for me.
The payoff comes when he spots something that's not on any star chart. But that's not all.
Final test. A comet's got to move.
If it doesn't move, then it's just another star. But because comets race around the sun, the movement can be detected in a matter of minutes.
Most comet discoverers would like to see their comet become a real beauty. There's more excitement. If it's a faint thing that hardly registers in a telescope, it's not so exciting at all.
If you want to see one of Bill's comets with your own eyes, set up your telescope in about 60 years. One of his discoveries will be back then. The next one returns in about 120 years. In the meantime, 76-year-old Bill Bradfield says he'll keep hunting. But no matter how many comets we see from the ground, to really understand them, we must get closer. Today, Bradfield and other comet lovers have their eyes turned to Utah. They're about to find out if the 7-year Stardust mission has been a success or a failure.
Oh man, I'm stoked recovering something that's coming that far out from space. It's going to be pretty cool.
The Stardust capsule will come hurtling back to Earth 10 times faster than a speeding bullet, landing like a fiery ball over the Utah desert, if all goes according to plan. The success of the mission rests with the Stardust recovery team. They're training to the point where they could probably do this in their sleep.
Okay, we're all done.
And that's a good thing, because they will have to locate the recovery capsule in the dark dead of night. To help do that, their helicopter has been equipped with a powerful light called a night sun. Speed and timing is key. Any delay will greatly increase the possibility of contamination. The cone-shaped vessel has logged almost 3 billion miles on its 7-year journey. So the capsule will be stored in 2 hermetically sealed bags to stop potentially noxious gases from escaping, and to keep the Stardust particles free from earthly contaminants. While Stardust's capsule heads back to Earth, the dream of future comet investigation heads deeper into space aboard the Rosetta spacecraft, the European Space Agency's most daring plan ever. The Rosetta probe was launched into space in May 2004 aboard an Ariane 5 rocket. Its goal? To bring down its dishwasher-sized lander on the body of a comet the size of a small island, documenting its evolution as it heads towards the center of the solar system, shedding its icy outer layer, coming to life under the sun's glow. Rosetta will reach its target in 2014. It's a mission so far in the future that scientists keep a life-sized model of the lander to work on. Stefan Ulametz is project manager.
We need to make sure that after 10 years of cruise, people still know how to operate the lander, but also if some problem occurs, how to solve it and what could it be. And in order to have a model here on ground to test commands and also to play a little bit.
Scientists and engineers have done everything possible to prepare their small craft, even though they have no idea what the surface of their target comet will be like. Previous missions to comets like Stardust and Deep Impact have raised even more questions and concerns.
Oh, of course, it was exciting to see really the cometary surface and to think about how would our target comet look like, and would it be similar, would it look like this? And then, of course, the second thought is, what is this surface like? Is it very soft? Is it hard? Could we handle it with the lander?
The Rosetta team built its lander to survive any surface.
So it could be an icy, grainy dust world, but it could also have more bizarre ice glacier structures with more snow, more dust.
An active comet could be treacherous, shooting out jets of gas and dust as it gets closer to the sun. The craft will orbit the comet for 6 months, analyzing its icy surface, searching for a good place to touch down.
One thing is for sure, of course, the gravity is very, very low,
making for a very tricky maneuver. If the Rosetta lander comes in too hard, it could bounce back into space and disappear. The solution: 2 harpoons will shoot into the comet's surface, anchoring the lander to the comet.
We want to see the stuff itself, we want to grab it, we want to, well, I would say feel it there, you know, and we have instruments which actually can do this.
The lander is equipped with 10 such instruments, cameras that act as eyes, a drill that can pierce the comet's surface, analyzers to test gas and particles, even a small oven to heat up samples. Scientists will sift through that data, searching for signatures of organic molecules that will help answer the mystery. Did comets seed life on Earth? That is, if the lander survives its increasingly dangerous ride. As the comet heads toward the sun, it could begin to violently disintegrate.
The lander may well be hidden under dust grains or even ejected together with the piece of junk it is sitting on into space. This may happen, but hopefully only after we have all our scientific results we expect to get.
Rosetta will have a front row seat for a year, observing and collecting data, surely revolutionizing our understanding of comets. As the Rosetta craft speeds through space toward its rendezvous, Stefan Ulemetz will be anxiously awaiting word from Stardust.
Stardust will allow us to analyze cometary material here on ground in our lab. And this is the dream of each cometary scientist, to do this at home in the lab. And we will be able to use this information to optimize our instruments on the comet.
For centuries, comets were mysterious and beautiful visitors to Earth. We've been forced to watch them from afar. Now, with Stardust and Rosetta, we have become the travelers. When we come back, the countdown is on as NASA's Messenger returns to Earth, facing its final challenge.
This is a spacecraft. You can never say nothing can go wrong.
It's all come down to these last few tense minutes, the final leg of an unprecedented 3 billion-mile, 7-year round trip through the solar system. And there's nothing more these NASA scientists can do but wait.
Mission Manager, Spacecraft Team Chief. Yeah, I've just been talking to our engineers here, and that the state that we are in is, in fact, the correct state. A bit more reassuring.
Then, another piece of good news. The capsule has successfully released from the spacecraft.
And at this time, we can verify that the cable cut and release global variable has switched to 1.
But there is still plenty of work to do. The Stardust capsule must survive its fiery high-speed re-entry into Earth's atmosphere.
All stations, SRC just descended through 15,000 feet. Again, the main chute's going to open at around 10,000 feet.
As the capsule entry begins, 3 helicopters equipped with ground-tracking infrared sensors are on their way to a staging area in the Utah desert.
All stations, this is Project Manager at UTTR. All 3 helicopters are at Pad 11.
Scientists anxiously track the capsule's re-entry. With its sudden drop in speed, it becomes clear that the main parachute has deployed at 10,000 feet.
This is the calculated time for the main chute, and we're seeing deceleration.
Wow.
Whoa, it's coming right at us.
Oh, my God. It's coming right over here.
All stations, main chute is open. We're coming down slowly. Expected landing in less than 1.5 minutes.
Moments later, it touches down.
All stations, we have touchdown.